Welcome to Hot Chips 23. Session 8. Video.
All right, our next session will be two presentations on video processors. Our first talk will be given by Dr. David Moloney. He received a Bachelor of Engineering from Dublin City University in 1985 and a PhD in Engineering from Trinity College, Dublin in 2010. Since 1985, he worked for Siemens in Munich, ST Microelectronics in Milan, and as a DSP IC designer before returning to Ireland in 1994 to co-found a series of startup technology companies, including Parthus and Solansis. Watch out for what's going on back there. Okay. Pardon me. Dr. Moloney is currently co-founder and CTO of Movidius, a fabless semiconductor company headquartered in Dublin and focused on the design of software programmable multimedia accelerator SoCs. He holds 18 US patents and is published in a variety of conferences and journals. Dr. Moloney.
Good afternoon. Can everybody hear me? Okay, I'll grab my pointer here. Okay, so I'm going to present our programmable media processor. I think it could be interesting for some of the robotics applications that Steve mentioned in his previous presentation. The top line figure there is 1 teraops per watt. Obviously, that's not 32 or 64-bit, but it is nonetheless representative of what can be achieved with this platform. So we're based in a remaining on the beer theme from earlier on. We're based in a location that's better known for Guinness than for semiconductors. But we started life back in 2005, and initially we were looking at gaming acceleration, things like game physics, game AI. For mobile platforms, we were looking for a niche, and we developed our specification for a chip, and we went out starting to talk to mobile phone companies, primarily based in the Far East. And they said, yeah, all very nice stuff, but we're not going to pay extra money to put in a gaming acceleration chip. The real problem we have is video. So we have basically we went back to the drawing board and added all of the video processing capabilities to our platform. Our platform is based around our own unique processor technology. At the time when we developed our chip, we didn't, let's say there was nothing on the market really that offered the processing capability that we required for things like game physics in real time. And we basically developed everything from the ground up. We managed to do our initial prototype device containing 8 of our Shave processor cores in 65 nanometer with a 5-person team. Obviously, the usual thing of outsourcing physical design and so on. We're a fabless semiconductor company, but it just speaks to the merits now of the tools that are out there and the possibility to co-design silicon with your applications. And currently we're going, we'll have consumer products, or let's say our partners will have consumer products for this holiday season in the likes of Best Buy and so on, based on our current 65 nanometer chip. And I'll talk a bit more about some of those applications that we're targeting as we get in. And finally, I'll talk initially about the processor, then about the SoC that we have based on that in 65 nanometer, something about the applications, and then about the next generation chip and how we're busy designing that and what we learned primarily from our first chip design. So if you look at the video processing requirements, starting from the initial phones, Japanese, and I suppose most notable the Nokia 6630, introduced in 2004, it was doing fairly what was considered very advanced video processing at the time, and was able to play back QSIF video. If you look at what's happened over time, we've very rapidly reached the position now where we're able to do 1080p at 30 frames per second, playback and record on the likes of the LG Optimus. And very rapidly we're evolving to the position where we'll be doing either 30 or 60 frame per second 3D stereo video record and playback, and there are even suppliers now who are starting to talk in roadmap terms about 2K video on devices in the next in the next year or so. So in order to address those requirements, we basically had looked at game physics. We had a whole series of game physics algorithms that we needed to support at 32-bit floating point, and we essentially have now we extended those, adding integer capabilities at 8, 16, and 32, and also a bit integer, and also we added FP16 to be able to support OpenEXR format that's very good for high dynamic range photography, but by the same token video processing, and it's actually very useful in a whole variety of different applications. So we came up with a SHAVE as an acronym for streaming hybrid vector architecture, and essentially that allows us to offer a whole series of RISC type instructions, DSP type instructions, and even streaming GPU type instructions with an overall kind of variable length VLIW style instruction. And it's essentially tailored for optimal number of operations per milliwatt per dollar. So we can achieve around about 20 gigaflops single precision in terms of arithmetic capability at around 300 milliwatts. We have particular support in there in terms of offload engines for graphics. We have a texture management unit, and also we have specialized hardware to allow sparse data structures to be supported. So we can support fully random accessible sparse data structures in memory, which is very useful for things like game physics, but equally for the coefficient matrices that are used in H.264, for instance, encode and decode. So we, similar to the ARM processor and the Itanium, we have predicated execution and branch delay slots in order to eliminate branches and maximize performance. It's especially important for us given that we're operating at a very relatively low clock speed of 180 megahertz in 65 nanometers. And we've designed the architecture also from the outset to be a good target for compilers, and I'll talk about some of that in the following slides. So I think I mentioned already that we support a whole series of RISC style instructions, all that's necessary to support a C compiler. We have DSP style instructions that allow us to do a single VLIW word FIR filter. We also support for things like FFT, Viterbi, and so on. We can support the modulo addressing modes that are required for things like FFTs. We can also support Viterbi and so on. And we have a very wide 128-bit vector unit in order to allow us to, let's say, reduce the low power implications of having to fetch instructions, so we can achieve more optimal power performance from that point of view. We have a graphics unit associated with each SHAVE processor that supports things like bilinear, trilinear interpolation and texture compression and decompression, and we have an associated L1 cache direct map to support that operation. So if you look in terms of the shave instruction set with respect to the ISA richness, it's somewhere in the middle between the rather small ADI Blackfin instruction set and something like IBM's cell processor that's more aimed towards high performance gaming and HPC. So if you look at the shave processor itself, we have somewhat similar to the organization of the cell processor. Each shave processor is associated with a local 128 byte slice of SRAM, and that's configurable in 8 kilobyte increments between instruction and data. So you can vary on a processor by processor basis the amount of memory associated to instruction memory and data memory. You can also see via the vertical interconnect that comes out of that left-hand 128 byte block, we can communicate with the full 1 megabyte of shave memory. The two neighboring processors you can access with zero penalty. The ones that are farther out, there's a delay penalty associated with those. And in fact, one of the things that we learned from looking at our applications that we wrote, and I'll talk about it a bit more in detail later on, is that we only actually really do the bulk of the communications with the two neighboring processors, and you can take advantage of that. And we are planning to do that in our next generation chip and cut down the amount of global wiring. You can see in there also we have the 3 separate units. We have an integer unit with associated 32 entry by 32 bit integer register file. We have a 128 bit vector unit with 32 entries in the associated register file, and we have a scalar register file that so the combination of these two units allows you to do streaming matrix vector products, which was very important in game physics applications, but is also important in many other applications. In order to keep the beast fed with data, we have 2 64-bit load store units that communicate with the SRAM tile, and we have a compare move unit, which is very important for generating predicates. So we can do 3 comparison operations per either 16-bit or 32-bit or 8-bit entry in the vector register file in parallel with the vector operation. So for things like game physics, where you want to do collision detection, you can do all that in parallel, and you can generate predicates for the predicated execution unit. As I mentioned previously, we have a branch and repeat unit that's used to do things like zero overhead looping, and we can do things like single VLIW word parameterizable FIR filter, which cuts down the requirements there in terms of instruction fetches. And we have a shared L2 cache and a DDR controller, and in package we have either a 16 or 64 megabit die that's stacked, so it's a known good die from a DRAM supplier. So the whole lot of this is basically put together in a single chip, and you can see we have very high bandwidths, not due to the clock frequency, which is only 180 megahertz, but due to the large number of ports from these register files and the width of the different buses around the system. So we can get very high sustainable throughput. If you look at the game physics solver that we initially used, we're able to achieve about 70% sustained throughput for that application, solving for about 300 joints in a rigid body model. So the overall 65 nanometer chip basically contains 8 of the shave processors with associated texture management unit and connection matrix memory. We have an overall 64-bit AXI bus that's used to talk to the various different peripherals. This is the second kind of Spark-based paper today, in that the chip or the chip here uses, as the overall RISC controller, uses a synthesizable Leon 3 core. And we have a large number of interfaces. We can basically support 2 cameras up to 12 megapixels at very high rate, equally 2 very high resolution LCD controllers. And then we have a large number of other peripherals. In order to keep the pin count down and allow us to fit into an 8x8 BGA, we have a large amount of multiplexing on the pins, so you can route out large combinations of interfaces to allow you to talk to various different application processors. If you're in a mobile phone, for instance, you can talk to Qualcomm or TI or other processors with no intermediate glue logic. And as I said already, all of the different processors communicated via this AXI bus. We have H.264 high profile CABAC support in the form of this NAL block here. And basically there's a whole kitchen sink of peripherals in there that you can use for pretty much any application. So if you look in terms of the overall processing, if you look at 8-bit operations, if you include all of the equivalent operations that are happening in the various different units here under program control, it comes to about 1 gigaop per watt. So about, given that we're dissipating about 300 milliwatts here, it's around about 300 megaops per at 180 megahertz. And if you look at the fraction of those that are arithmetic operations, it's about 181 gigaops per watt, again at the 300 milliwatt figure. And this obviously scales down, but you can still achieve at 32 bits floating in, that's fully IEEE compliant 32-bit operations, you can achieve around about 50 gigaops per watt there in terms of efficiency. This is just a kind of an expanded version of the same slide, just to show you the breakdown. And the horizontal numbers here are basically for the vector unit, the scalar unit, and the arithmetic and the integer unit. And obviously the integer ones only contribute to these 3 figures here. These are floating point numbers alone. So if you look at the overall die shot there, the whole die was placed and routed with essentially only 2 macro, or 1 macro that was done. That was the shaved processor with the memory, the 128K memory slice, and everything else then was routed flat. And the die is basically bumped onto an FR4 substrate that we custom designed, and then we wire bond the 16 or 64 megabit SD-RAM. It's DDR2 on top of that, and the whole thing fits inside an 8x8 package. If you look compared in terms of the power efficiency for the 32-bit floating point, we're basically at around about 50 gigaflops per watt, and compared to work that was reported in ISSCC this year and work reported by Intel a few years ago on their teraflop processor, we're considerably ahead of those numbers and this figure basically would include all of the peripherals as well, and the SD-RAM. So essentially, what we do here is, as a small company, we didn't want to develop N different mask sets. We wanted to develop one single processor with many different software applications, so we could attack lots of different verticals, but without having to do a different chip for each one. So we're able to do 3D capture, and in that 3D capture application, we can remove any requirement for precision, tolerance, alignment of 2 cameras for stereo video, and we can basically null out those the manufacturing tolerances using SURF to find features and match those features between the 2 cameras and do 1080i video encode, all within the 8 processors that we have at 30 frames per second. Similarly, we can do video edit applications, and there we have an API that works together with Android software that would run, let's say, on an application processor capable of supporting Android. So this would the GUI and so on runs on the ARM, and everything else runs via an API on top of an interface to our chip. We're also able to do 3D video record. And another interesting one, and this is the one that's going to market and will be available commercially from one of our customers later on this year, is basically real-time 3D or 2D to anod-lift conversion. So you can, instead of throwing out your existing $1,000 TV that you bought a couple of years ago to get 3D capability, you can add a $99 box on, and basically be able to watch 3D on your existing TV with color-coded glasses. And just to put this in perspective in terms of the amount of processing, we basically designed all the software in-house. We have a compiler and all of the other tools. But basically, if you look at across the 8 processors, you need less than one of the processors to do an AAC encode or decode, but 3 to do 1080i H.264 decode. And if you look at the full kind of anod-lift conversion application that I mentioned there, you use for 2D to 3D conversion to kind of get a pseudo 3D that you can do from motion. It takes one of the processors. You need about 6 to do the anod-lift conversion and 1 to do the resizing for the output. We can also do things like for the camcorder, you can do all of the rectification and auto-convergence on about 4 of the processors. So very programmable and very capable. In terms of next generation, we've basically been doing, we have developed our own simulator as part of a European project with an OpenCL API, and we can support a subset of OpenCL on there for certain critical primitives. And we can basically build different versions depending on the number of cores that we have, and importantly predict what the power is, not in absolute sense, but in relative sense, with a few % accuracy using the simulator that we built. And essentially the architecture that we're working on now in 28 nanometer will be capable of about 450 gigaflops per watt at 32-bit precision at about 800 megahertz, and that still contains all of the power islands and so on that we have to allow us the flexibility in terms of and granularity in terms of power that's required for mobile phone applications. We have a much larger stacked SD-RAM, and in our learning from what we'd learned before in terms of communications patterns, we've divided our architecture into clusters of 4 processors that have a very good communication locally and less communication globally, and this is basically more than able to meet our communications requirements and applications requirements, but greatly simplifies the design of the overall chip. So I'll just put in my plug for the European project that we're part of here, and it's been invaluable to us as a small company in terms of being able to develop the necessary infrastructure. Thank you very much.
All right, we have some time for questions. Again, please come to the microphone, state your name and affiliation.
Hi, my name is Mujibur Rahman. I'm from Texas Instrument. I have a simple question. 16-bit floating point is IEEE compliant, or internally you convert 16-bit to 32-bit and make it 32-bit?
No. I mean we have we have hardware support for 16-bit floating point. There's no IEEE standard for 16-bit. But all of the modes, the same 4 modes are supported in our 16-bit floating point as would be supported. I'm talking about now IEEE 754, not the latest standard, but where it operates in exactly the same mode as the 32-bit floating point does. But it's, at the time we designed it, there wasn't a standard for 16-bit. What we have done is we've worked with Kronos on 16-bit floating point support within OpenCL, and that's something that we are compliant with.
Oh, okay. Thank you.
Okay.
Any other? Do you have a question? Okay.
Yes, this is Jose Flores from Texas Instruments too. And you quoted almost 50 gigaflops per watt.
Yes.
And basically, you are obtaining all that efficiency with parallelism. I didn't hear you mentioning about the adaptive voltage scaling or any other technique.
No, we didn't use any adaptive voltage scaling. What we did was we used TSMC's low power 65 nanometer process. Each processor is in its own power island. We have a total of 11 power islands on chip. And what we did was, I think Tylera made a presentation here the other day. I mean, Anant Agrawal basically talks about this idea that, you know, beyond the sweet spot, you start to pay, you know, quadratically in terms of power for every kind of megahertz increase in performance, and we took note of that, and we designed, you know, our chip for a relatively low clock rate of 180 megahertz, and looked at maximizing parallelism rather than trying to run very hot for a very short amount of time, and it's paid off for us in that we've achieved very high degree of power efficiency. But beyond, there's nothing beyond basically power islands and low clock rate and attention to design.
Okay, thank you.
This is Liang Peng from Intel Cooperation Architecture team.
Yeah.
So I have a question. It looks like you are going a little bit more than the cell processor by adding that texture engine there. And so I just wonder whether you are also considering the other part of the fixed function pipeline of the GPU, such as rasterization pipeline.
I mean, the GPU functionality that we have in there is more as a consequence of, I suppose, marketing decisions. I wouldn't claim that our chip is a good replacement for a standalone GPU. What it is good for, however, is you can use that bilinear and trilinear interpolation for a large number of other applications. For instance, if you want to map video onto a mesh, so you can see, you know, I don't know, some video mapped onto a sphere or something that's rotating. It's convenient for that, but I wouldn't claim that we're a you know, high-performance graphics processor. It's probably around about a third of the graphics performance that you'd see on a lot of the high-end application processors.
Okay. Last question.
Okay, Moinul Khan from Qualcomm. A couple of questions. So one is that, do you still have the CABAC in hardware?
Yes, that's the NAL block that I showed on the right-hand side at the bottom. And that NAL block basically supports the CABAC in hardware. Yeah, I mean, there's you can't parallelize that, and you know, we're not pretending that you can do everything in software, but you can do a lot.
Sure. And also, any comment on the area for H.264 decode for 1080p?
Well, I mean, we don't have we do all of the H.264 decode in software. So essentially, we're not. You know, you can do H.264 1080i high-profile decode on 3 of the processors that are on chip.
Just how much is the area investment? I was just curious.
Well, that's kind of commercially sensitive, so I'd prefer not to mention the figure. But
okay, thank you.
Okay, let's thank our speaker.
Thank you.
Okay, our next speaker is Hong Jiang from Intel. Dr. Hong Jiang is the Chief Media Architect in the Visual and Parallel Computing Group and the Intel Architecture Group at Intel Corporation. He's a Senior Principal Engineer and has been with Intel over 14 years. And he is responsible for the media architecture of Intel's high-volume personal computer products.
Thank you very much. It's an honor to be here. Today I will be presenting the Intel QuickSync video technology in the second generation Intel Core processor family. Here's the legal notice you have in your pack. I will cover first the processor graphics overview, then spend most of the time looking at the detail of the Intel QuickSync video technology, then give the result and the conclusion. Here's a block diagram of the second gen Intel Core microprocessor. In the next session, you will see more detail of this microprocessor. Here, I will only focus on the processor graphics integration. We put the display engine in the system agent that is very close to the memory controller to provide the ISOC support and also have very good power management. And we also put the main graphics engine, the graphics render engine, on the ring to make it a first-class citizen service in the system. Integration of the graphics on the main die have a lot of benefit. Here's a few highlights. We moved the graphics design from the N+1 process to the latest 32-nanometer process, give us the frequency, area, and power benefit. We also share a lot of system resource together with the CPU core, like the last level cache. We also have, in this design, we put a very special design for every single graphics stream. We have control whether we can use the cache or not. That's fine level control allows the software team to tune for performance and power. A major feature here is the dynamic core and graphics power sharing and power distribution. When workload is in the CPU core, power supply go to CPU, vice versa, power supply to the graphics. The fine-grained power management really help us to get the maximum performance with very limited power supply to the die. And we also designed the graphics core to have a pretty high frequency, 1.35 gigahertz. Here's a picture behind the graphics render engine that's connected to the ring architecture. So over here, the primary core of the design is array processor. Today's GPU all is based on the parallel computation. And in order to achieve the very high compute efficiency of the massive thread machine, we have to handle very good efficient thread scheduling and resource management, and also have to provide very good I/O support to the compute array. The front end of the machine, we call them fixed functions. We have a 3D fixed function and a media fixed function. And the 3D fixed function follow the DX OpenGL compute pipeline that are going out standard. The media function is much more general purpose, just mostly handle the thread generation and control. So at a given time, we can use the EU array for either 3D operation or media operation. In the diagram here, I used the color code. The green color means the resource share between the two modes of operation. And the 3D color and the media separate function unit. You can see that a lot of major computation are shared between two modes. And we do, for the EU array, we have a very specified instruction set to deal with pixel shader compute in 3D, and also instruction set just dealing with the media computation. I have detail later on. The share function are the one that provide I/O service, load and store. But it's really just not a simple load and store. Through the data movement in and out of the system, the compute of filter compute is also applied. For example, texture sampling, you do a bilinear filter or trilinear filter operation. And for video, we also have a lot of compute operation inside this media sampler or media backend pixel operations. And we also have this common data port that allow us to do the scatter gather and the block-based memory load and store to really make the efficient data movement into the array computation. And in parallel, we built this multi-format video codec. And I'll get into a little more. It's a very important feature for video processing. So going down to the detail of the PG execution unit, that's the processor, one of the processors in the processor array. So in the block diagram here, we show the 3D pixel shader type of operation where the data flows through the system in the very regular fashion. We also have the different mode through the same computation unit by doing the vector matrix-based media operation. So instruction-wise, if you look at the core, we put 5 hardware thread per EU. With hardware thread, there's a 0 penalty thread switch, allow us to have enough thread to keep the IPU pipeline busy. And very large register file, 128 256-bit register file, really holding the data close to the compute, have very good power performance efficiency. Instruction-wise, the IPU is 128-bit IPU, can put 4 floating point or 8 byte word fixed point operation in there. So for 3D operation, we optimize for pretty much, if you take a shader instruction and map to the hardware, it's almost one-to-one mapping, very efficient one, doing per channel predication or flow control. We have fmag and also the mass function embedded into the EU array. And another part really for the media operation is the mode of different mode over here. Here is the fundamental architecture difference here, unique compared to traditional SIMD design, is that the crossbar. We build a full byte crossbar for both operand that allow us to, at the per instruction level, control data access from the register file to the compute pipeline. This really solves the fundamental problem for SIMD compute, data shuffle, format conversion, those very expensive operation, where we do that on the fly per instruction. And in this kind of operation, the register file is not just 128 registers. We treat them as a 4 kilobyte RAM per thread. And we have a very rich addressing scheme we call the 2D region-based addressing that allows the per instruction level selection of element to the vector computation. And for the large register file, we also support the index-based register access. Remember, you just have a pointer to the memory to select the data into the compute. Since this is just the introduction of the architecture, I have to move on. I can spend the whole afternoon talking about this operation because I designed this part myself. Okay, now the main topic of today is quick sync video. Before I move on, just ask 2 questions. Has anybody here done some home video editing at home? Just show of hands. A few. Have anybody tried video conferencing using something like Skype? Yeah. So video usage is very common usage in the PC, at least in the PC. Actually, now it's going to a lot of mobile devices. And a few years ago, when we look at the experience, it's really difficult. The video quality is low. The machine is so slow. You actually, when you try to edit the video content, you spend the whole weekend trying to play with the software and sit and wait for the computation to complete. So people wait for machine. So we want to really solve the fundamental problem for video editing, video conferencing, by providing the fundamental capability in the machine that really solve the problem so that we don't have to wait for those issues. And there's also transition from standard definition to HD definition. So there's a huge amount of 6x pixel increase from traditional pixel to today's high definition video. So basic building block is a video decoder, video encoder, and video processing. I'll talk more about this later. So 5 years ago, when we took the project, actually took us a very long time to build a processor. There's a few challenges we notice here. We have to meet the requirement faster than real time. And here I'm talking about the HD video operation, encoding, decoding operations. And to do that, we have to maintain high quality. The visual quality definition already defined by today's slow but high quality software. In order for us to convince the customer to use a hardware or hardware accelerated solution, we must maintain the high quality in order to while achieve the performance. And transition to mobile computation also requires to do this in a very low power environment. And we also have a charter to leave enough compute cycle back on CPU to really perform the high advanced functions. How do we do that? We take a multifaceted approach, look at different problem, and look at over there for the performance. We talk about the dynamic power delivery. so that we share this GPU, CPU, give enough power when the workload is in the right place. And we build a parallel engine to achieve maximum parallel compute. And also, we focus on the implementation of hardware accelerations, fixed functions. For the power limitation, for the compute limitation, that's the approach we continue to drive the performance. And meanwhile, for quality, we have to maintain quality. Here, particularly for the encoder, we have to give enough flexibility to make sure that there always continue innovation in the software world to continue to improve the quality, address different applications. So we balance out the programmability with fixed function. By focusing on the fixed function also allows us to address the other two problems. One is power. Fixed function is much smaller. We can reduce the C time for the operation, aggressively reduce power. Another big power here is platform power, C time, the package C state. Deliver high performance actually also give us the power by doing something called reach to halt. We run the operation and finish the operation, go to low power state for the complete package. And let's talk about decoder, encoder, and the video processing. First one, decoder. For every single decoder, you must provide bit-precise solution according to the coding standard. So for that kind of process, standard is pretty much stable. Therefore, the best approach is to go for our hardware decoder. We define this multi-format codec. The full hardware decoder is in there. We support the mainstream MPEG-2, VC1, and AVC coding standard. AVC standard we actually make it pretty flexible to support the late coming multi-view video coding as well. And the front-end decoder is a pretty common, pretty different, that the different coding have a different bitstream compression. We build separate blocks so that we can make the design and validation pretty easy. The backend of the decoder happen to share common data paths. We build a common data path for all the standard, and that's achieved a very high throughput, and also bring the area and power down in the operation. And we also build a stateless design here so that we can switch the content after one frame operation. You can switch a different video stream or different coding standard. Everything is very flexible. Stateless is really important to make the PC broadly useful. And synthesize to pretty high frequency as well. That's another design challenge we have. That's decoder. Encoder is a different beast, and encoder is a place people innovate, place have a lot of art and algorithm innovation. Here's a pipeline for encoder from left to right. That's you have input a current picture and reference picture, doing the compression, output the bitstream for the current frame, and also output the picture for the current reference for current picture for the future reference. And I highlight a few blocks over here that is a major challenge for design. The first block is motion estimation. And that's the place most compute for encoder is happening. Search. You have to find the right search in the spatial domain, and a lot of computation is involved. And another two part is mode decision and read control. Those are the place a lot of algorithms are applied so that you have to provide the programmability for those places. Another pretty nasty problem is entropy coding. I think previous talk discussed. Keyback is a nasty problem for general purpose processor, and it's impossible to map that on a pixel vector parallel processor. So looking at the problem, here's the solution we do. We design a two-stage video encoder. The front end, I call it ink, which is the front end operation, and back end, we call it pack. So by slicing the encoder operation to two stages, we map them to a different design part to maintain the flexibility and performance. So the ink part is mapped to the program EU array, that the massive compute motion search is handled by the hardware acceleration put in the media sampler. And the rest of the machine is still writing the code running the EU array to get all the different algorithms to develop an algorithm. The pack part is relatively stable. We actually load that into the fixed function MFX codec engine. And we reuse the decoder hardware to make the whole thing work. And you can see that every single encoder, they have decoder inside because you have to deliver the bit-precise reference for the future frame. And we also allow the ink and the pack to run in parallel to have the maximum throughput. So the multiple engine parallel compute really is a key to achieve throughput. So now talk about encoder. First, the pack part. The pack part, we mapped, here's the diagram, a very similar one is whole picture. I use color code again, showing the common shared blocks between the encoder and decoder. And now you can see that I just add 2 more major blocks, forward transform and entropy encoding that complete the encoder pack in the hardware. And we also design pretty configurable data paths because encoder and decoder data path configuration is different. We actually designed this hardware structure to support both modes of operation. For pack hardware design, we have one design objective. We want the fixed function design to be forward-looking so that we have the solution in place, continue to support the software innovation to try different algorithms. For example, certain algorithm for video conversion, certain algorithm can use for video conferencing. They are all different. And make sure that the hardware is there, can be done for the future. And that's a major design challenge here, because if you don't have an encoded build, how do you test the hardware, make sure the hardware works? And the two approaches we have here really solve the problem. One is the partition of the ink and the pack. We separate pack from the ink, so that's one independent over here. Second one is we have a very unique innovation here is to use a common validation methodology between the decoder and the encoder. For decoder, you must provide bit precise results for every single corner cases. We apply this rigorous validation process to the pack encoded design. That's pretty much flush out the majority of bugs we have in the design before we have the silicon back. Yeah. So for the ink part, I only focus on the parallel compute part. There's a basic motion search is done by the hardware. And in the parallel compute, encoder actually is a key challenge on traditional parallel compute. There's data dependency. In the picture here, I showed a frame, and each block is a micro block. If you look at the current micro block X, it has dependency of A, B, C, D neighbor micro block. So it is not a pure a dumb parallel problem. You have to resolve dependency in the parallel in the system. So by walking the wavefront order from the upper left corner to the lower right corner, you can discover more independent blocks that is you can do parallel compute. But you have to really resolve this dependency in the real execution. Otherwise, the information is lost. If you look at some GPU-based design, you have to cut people to achieve a higher performance, have to cut corner, then those dependencies disappear and the quality suffers. Yeah. So over here, we developed something called explicit parallel programming model. Each microblock is mapped to a hardware thread. And in each thread now, we use this EU instruction set, can do vector matrix computation, and also can do the scalar-based computation in the same code. And this, again, is not the traditional GPU programming anymore. And the thread is dispatched in this wavefront order, and we use a hardware scoreboard to resolve the dependency of the different thread. Yeah. Another important one is in order for the design to scale with the different size of the parallel machine, we have to also have the shared memory, and the scoreboard has to apply a broad array of data execution units instead of the subset of those in different architecture. So here's a hardware scoreboard solution to this problem here. We assign each thread ID, and the ID is a two-dimensional ID XY. And now you can describe the relation of the different thread by introducing the delta X, delta Y relation, spatial relation. And then the hardware will describe this kind of relation and resolve the dependency in the thread dispatch. So we implement this same scoreboard in software in the past, and we have a message gateway. I haven't get down detail that allow the thread-to-thread communication, and that one took about 200 cycles to resolve the dependency. And in hardware scoreboard, make that a few cycles. Yeah. So here's the point: design we tend to start with a software solution. Once we know and stabilize the software solution, move that into the little bit more hardened that solution to achieve a higher throughput and higher power efficiency. And scoreboard type also is applied to both 3D And when you render 3D pixels, they have to be rendered on screen in the right order. Here, we apply the same scheme here for video. When you have to render those microblocks in order, we use a scoreboard to solve them in order too. Two kind of a scoreboard. One is a stalling scoreboard. The thread is stalled until its dependent thread cleared the way before we can launch the new thread. Another way is more compute efficient. We allow thread to be launched, and only the critical session is stalled until dependency is cleared. So that gives a higher throughput there. Yeah. Now talk about video processing. Again, same technology. We applied those in the past in the EU array, writing our software and deliver the quality and also performance. Then we harden that into the hardware. We put that stuff instead of putting those functions in the dedicated hardware, we actually put it into the co-processor around the EU array. So media sampler have a lot of function here, and media pixel backend also have a function here. This allows the software to create a different pipeline, very flexible pipeline by building different software pipeline. So for example, we can build a video post-processing pipeline for playback, or build a video pre-processing pipeline for video transcode. Now, putting things together, now we can see we can achieve high-performance video transcode. We notice that decoder, video processing, and encoder, we all have hardware acceleration pretty much for all the stages of operation. And we deliver the software through the Intel Media SDK. A middle-level software have really make the application call to use hardware much simpler. Instead of, they don't have to really know how the real underlying work is done by the hardware. And also, the performance from the hardware cannot be realized if you don't have a good software. Here's one example here. We designed the asynchronous transcoding operation flow so that by providing certain queuing in the pipeline, all the decoding, processing, and the encoding can run in hardware in parallel to saturate all the machines we have in the system. Now look at some data. So when we talk about performance, here's our decoder performance. And for 1080p performance, typically when we talk about performance, we think about one HD, I'm watching one HD is 30 frames per second, maybe a picture-in-picture at real time. And the performance we deliver with this solution, we hit about over 20x performance of real time. We're talking about a few hundred frames per second rate. That kind of performance is really useful for two things here. One is a fast video transcoding. For transcoding, you have to decode and encode. When you transcode HD content to a smaller resolution, sometimes you become decoder bottleneck. We just designed the decoder to be fast enough to not be worried. Second benefit is, again, power, reach to halt. And we can reduce the packet state much smaller by complete work really fast. And those kinds of performance also really free up a big space for the innovation in the application space. In the old days, people tried to write software to make the playback work, right? Now playback is all handled. This kind of performance is there. You really allow people to write different applications in this space. Now talk about the power efficiency for the video, quick-sync video transcoding here. And boost performance and power showing here. This is HD 1080p to 1080p ABC transcoding, or 1080p to 720p video transcoding. And the baseline I used last year's last generation process as normalized to it. First, look at the performance. The raw performance here for transcoding is 5x real time. Remember, our initial target is faster than real time, and we deliver much faster than that. Yeah. And also, the performance pretty scale well. When we have a 720p target, we deliver almost a linear scale to the number of pixels in the target space. And also, the power performance efficiency in terms of performance per watt, and we deliver 6 to 9x better than the last generation. Yeah. So in conclusion, Intel QuickSync Video is really a unique video processing transcoding solution built on top of the processor graphics. We balance out the programmability and the fixed function to achieve the quality, performance, and power. And those fundamental capabilities we built here is not limited to just the transcoding one usage. Actually, can be used broadly in many, many other applications. Here's two examples. Intel Intra 3D technology, which is Blu-ray stereoscopic 3D playback. we have this decent performance, have enough headroom to do very low power 3D video playback. And also the very fast transcoding performance, encoding performance is also used, the hardware is used by the second generation Intel wireless display to allow us to move from 720p display to full HD display resolution. Thank you.
All right, we have time for a couple questions. Again, please come to the mic and state your name and affiliation. I'll start out with one. So you mentioned I believe it was race to weight.
Race to halt.
Sorry, halt.
Yeah.
And so I was curious, so with voltage scaling, there's some trade-off there between balancing the leakage and active power. Does your system, how do I say, does it scale the voltage and slow down a little bit to balance that?
So I think the design here actually have a different operation point. For performance, we go for voltage scaling to give a maximum performance under the power budget of the chip. And for your low power operation, actually we are not operating in that mode. That's we call turbo mode. We operate on the VCC min as the most power efficient mode as we can. Even at VCC min, we still have enough performance to race to halt. Right? So we're not racing too much. If you raise the voltage too much, you burn too much power. We actually, for a lot of mobile operations like playback, we run at the optimal performance point than a southern machine, because we are the small part of the overall die. So keeping the overall die down to lower power state is critical to bring the whole CPU power down.
Okay, thank you. Yes?
Hi, Charlie Demergent, Semi-Accurate. The cores that this goes into have a wide range of EUs available. I think it's 6 and 12,
yes.
And a very wide range of clock frequencies, and on top of that you have a very even wider range of turbo frequencies. Was the QuickSync designed to allow all use cases like 1080p to 1080p encode, decode, or transcode at the lowest of those, like a 6 EU, no turbo, low frequency? Or
yes.
Are there any limits? Okay.
Yeah, I think we designed actually initially, remember the objective is fast and real time. And in order for us to deliver fast and real time and also very low power, we actually deliver much higher performance than the stated performance. So we run the VCC min at say 800 megahertz. We still have plenty of performance left over to achieve those usages.
Thank you.
I have a question on the power management. You mentioned that you use a 5-grain power management. Can you elaborate how many power islands you have on it and the granularity of your power domain?
Okay. So for the scientific design, the second gen core design, we have a core space, on-core space, and also the PG, graphics space. Within the graphics space, we did not do further fine-grained power plant. But the fine-grained power management is in the sense that we can control the power state as a much finer grain. For example, we can control the power state of PG per workload. We have a different workload, adjust different power state for the different workload. From the dynamic point of view, it's a fine grain.
It's for the dynamic power.
Correct.
Thank you.
All right, let's thank our speaker again.
Thank you.
All right, that concludes our video session.